Here's one example of information you can get from an orbital. This one tells you, this is called the radial distribution function. You can obtain that from the orbital. And a plot of the probability of the radial distribution function for the 1s and the 2s orbital of hydrogen are shown here. So this is for an electron in a hydrogen atom. Okay. And as you can see, for the 1s orbital, this tells us the probability, how the probability of finding the electron depends on distance. So you can see here for an electron in the 1s, this is r, distance from the nucleus, in picometer. A picometer is 10 to the negative 12 meters. Okay, so the probability increases as you move away from the nucleus, reaches a maximum value, and then the probability goes back down, and then goes back to 0. So probability of finding electron very far away would approach 0. In this particular case, you'll find, okay, if you examine this graph carefully, that the most probable distance right here of the electron is 52.9 picometers. Okay. Now, this is a distance that was predicted earlier by Bohr when he tried to explain the spectrum of hydrogen using the well-defined orbits. This was what Bohr found was the first allowed orbit under his model. Of course, like I said, the idea of orbits is not acceptable anymore. But this number, since this was the radius of Bohr's first allowed orbit, this is now known as the Bohr radius. And it's given the symbol A0, and that value is 52.9 picometers. So 1 Bohr unit of length corresponds to 52.9 picometers. Okay? Now, on this sketch, you'll find that if the electron were described by the 2s orbital, okay, the probability of finding it versus distance looks like this. So it goes up, the probability goes up, and then goes back to 0, and then it goes up again to a much higher value, and then it goes back down to 0. So this right here is the most probable distance of an electron from the nucleus of a hydrogen atom if that electron were described by a 2s orbital. So how would you answer this question? For which orbital is the electron on average closer to the nucleus, 1s or 2s? You can see r equals 0 is where the nucleus is. So further away, a 2s orbital describes an electron that's on average staying farther away from the nucleus. So the answer here is 1s. On average, electron in the 1s orbital is closer to the nucleus. In fact, qualitatively, that's how you would interpret. That's one type of information you can get from the quantum number n. Okay, 1s versus 2s. The smaller the n in general, the closer the electron is to the nucleus. You can actually calculate the average distance of the electron from the nucleus from the atomic orbital functions. In the case of a hydrogen atom or an ion that has only one electron, for example, He+, you have 2 protons and 1 electron in each He+, or lithium 2+, okay? You have 2 protons and you have 1 electron in lithium with a +2 charge. The average distance can be calculated to be, and you can see, you can get that information from the quantum numbers n and l. Okay, so it's n squared times 1 plus 1/2 times 1 minus L times L plus 1 over n squared times A0 over Z. Z here is the atomic number. That's the number of protons in the nucleus. So in the case of hydrogen, Z equals 1. Okay. For helium with a +1 charge, Z equals 2. For lithium, Z would be equal to 3. There's 3 protons in an atom of lithium. Okay, so Z is the nuclear charge in atomic units. That's also the number of protons. That's the atomic number. Now, if we're dealing with atoms with more than 1 electron, it's a little bit more complicated, but we can make an approximation by replacing Z by what we call an effective nuclear charge. Okay, and the justification for that is if you have other electrons, if you have more than 1 electron around your nucleus, then each individual electron is not going to feel the full force of the nucleus because it's going to be repelled by the other electrons. Okay, so it won't be able to come as, for example, in the case of a helium atom, if you have 2 Okay? Let's say you have helium. You have 2 protons in the nucleus. Okay, so, sorry. Let's say you have 2 protons in the nucleus. Okay, and you have an electron. Okay, this electron is going to feel the force of 2 nuclei if there was no other electron there. But if there's another electron there, it's going the attraction to the nucleus will be partially offset by the repulsion from the other electron. So it will be able to move a little farther away from the nucleus than an electron. So helium atom versus helium plus. Okay, an electron in a helium atom would be able to move a little bit farther away from the nucleus than an atom in an electron in helium plus. Okay, so this is the formula you can use to calculate the average distance. And basically, what's the result of applying this formula? Well, let's apply that. For which of these orbitals is the distance of the electron on average farthest from the nucleus? Let's just calculate. Let's plug in the numbers. Let's say 2s of hydrogen. So n equals 2, and L, remember, S, P, D, F, L equals 0, 1, 2, 3. So L equals 0. So let's plug that in. That would be equal to n squared, which would be 2 squared, times 1 plus 1 half, times 1 minus 0, 0 plus 1, that's L plus 1, over 2 squared, times A naught over Z. Okay, so that's going to be 1. That's 4 times 1 plus 1 half. That's 1 minus 0. That's A naught over Z. And you'll find that that's equal to 4 times 1. Oops, 1 plus 1 half. 1 plus 0 cancels there. 1 plus 1 half times A naught over Z. So that's 4 times 1.5 times A naught over Z. So that's going to be 6 A naught over Z. So that's the average distance from the nucleus. Okay, so we have 6 A naught over Z for hydrogen. And if you did the same calculation for 2p, for p, quantum number L is 1, so you plug in 1 here and you plug in 1 here. And you'll find for the 2p orbital, it's going to be 5 A naught over Z, the average distance of the electron from the nucleus. For helium plus, it's still 6 A naught over Z, except that Z in this case is the Z for helium, which is 2. So that's different from the Z for hydrogen, which is 1. Okay, so for choices A and B, you're talking about hydrogen. So Z for those is 1. So the average distances would be 6 A naught versus 5 A naught versus 6 divided by 2 here would be 3 A naught. So on average then, among these 3 possible orbitals, an electron will be farther away from the nucleus in the 2s orbital of hydrogen. Okay, and note here about 2s and 2p of hydrogen, you'll notice that they're on average about 5 to 6 Bohr radii away from the nucleus. Okay, so they're more or less the same distance from the nucleus, 5 to 6. In comparison, a 1s, the average distance for the 1s, is about 1.5 A naught. Okay, so that's at least 3 to 4 times farther away from the nucleus than an electron in the 1s orbital. Now, you can actually figure out the difference between 2s of hydrogen and 2s of helium plus because they have the same formula for the average distance, except that the Z value for helium plus is higher. So your helium electron in the 2s orbital of helium would be halfway, okay, from the nucleus compared to the same electron in a 2s orbital of hydrogen. And the reason for that is your helium electron is going to be pulled more strongly towards the nucleus because you have an extra proton in your nucleus. So if you apply that formula, you'll find that in general, electron is farther from the nucleus on average, because at any time it can be very close to the nucleus or very, very far away. So we're just talking about average here. An electron would be farther on average from the nucleus in orbitals that have a larger n. So the most probable region is, you say, is in a larger shell. So if you recall earlier, we said 1s in the first shell, the most probable distance is around 1 Bohr radius, and in the second shell, 2s and 2p, about 5 to 6 times further away. Okay? Now, within a given shell, the larger the L, the closer the electron is to the nucleus, on average. Now, we're talking here about orbitals describing atoms that have only one electron. So an electron in a 2p orbital of hydrogen would be closer to the nucleus, since this is L equals 1, and 2s would be L equals 0. So an electron in a 2p orbital of hydrogen would be closer to the nucleus than an electron in a 2s orbital of hydrogen. Okay, so which of these functions here represent 2s, 2p, and 1s? Okay, so we expect the 1s to be closest to the nucleus. So that would be that curve, the green curve. And then the blue and the red curve here would represent 2s and 2p. Which one is 2s and which one is 2p? Well, the blue would be closer on average to the nucleus, would represent an electron that's on average is closer to the nucleus, so that would be 2p. And then the red curve right here would be the radial distribution function for an electron that was a little bit further away from the nucleus, and that's going to be your 2s. Okay? So one thing you've realized from the previous slides is that the function that's associated with an orbital name is not the same in different atoms. Okay, so 1s of hydrogen, a 1s orbital of hydrogen is not the same thing as a 1s orbital in helium. It's not the same as a 1s orbital in helium plus, or a 1s orbital in some other atom like carbon. Okay, in general, if you're talking about the same orbital name, okay, the higher Z would, more protons in the nucleus would pull that, the electron described by that orbital closer to the nucleus. So here's a question. Which orbital describes an electron that is closer to the nucleus on average? A 1s orbital of helium plus or 1s orbital of H? Okay. Same orbital, right? But helium plus has Z equals 2, hydrogen has Z equals 1. So the electron in helium plus will feel a stronger pull from the nucleus, and so this would be closer to the nucleus.